All right. Hi, hackers. Wow, what a weekend. We know you all may be slightly or very much sleep deprived, so we'll keep this short. However, it is worth mentioning that the judges were very impressed with all of the solutions presented in the semifinals rounds. The dedication to energy and developing sustainable solutions is inspirational. Our final round will begin soon, but first we'll hear from our keynote speaker, our final keynote speaker of Energy Hack 2020, James Rincon. James is a manager in Avangrid's CEO office and leads corporate innovation. In this role, James manages strategic partnerships with top-tier universities, startups, and external technology partners, working to implement innovative technologies and business models to advance Avangrid's networks, renewables, and corporate areas. He also collaborates with Iberdrola's global innovation, sustainability, and quality team to share and leverage resources and best practices from across the Iberdrola global group. James, please take it away.
Thanks very much, Kelly. I'll go ahead and share my screen here in a moment, but small twist for you. What I have for you today is a presentation from the Chief Sustainability and Innovation Officer, Agustin Delgado from Iberdrola. So I'll keep that up for you, and I hope you enjoy it. Thank you for the invite today. It's been a pleasure to work with all the hackers and see your creativity and hard work. So enjoy.
Hello, my name is Agustin Delgado, and I am the Chief Innovation and Sustainability Officer for the Iberdrola Group. Well, thank you for inviting me to try to explain you how do we see the technology about hydrogen and what are the possibilities, and in the end, how far can hydrogen go in the future. So let's start. We're going to divide this presentation into like four main pillars: production, storage, transport, and distribution and use. And I think the fourth of them are very important to understand what is the role that hydrogen can play in the future energy system. Hydrogen production. The truth is that hydrogen is not something new. The world is already producing a lot of amount of hydrogen. Directly, it is producing 70 million tons of hydrogen, but also as a byproduct from the chloroalkali plants, it's being produced like 45 million tons of hydrogen. And all this is being used in the refining industry, in the fertilizer industry through ammonia, and also to produce some other chemicals like methanol and some others, right? The use of hydrogen in transportation or in the energy sector is really, really small. How can we produce hydrogen? There are different forms. The most important one is through natural gas, through a process called steam reforming. But also you can do coal gasification. This is done in countries with a lot of coal and with not that much environmental concerns like in China. And the biomass gasification and electricity are really a very small portion of the hydrogen that's being produced today. For sure, once you have the hydrogen as a feedstock, an industrial feedstock, you can produce ammonia through the Haber-Bosch synthesis. You can use it in a refinery, or you can use different methods to produce methane or even synthetic fuels. But this is very small right now. The steam reforming is the most used method to produce hydrogen, and it consists in a reactor that uses a high temperature where you put the methane, the CH4, together with water to obtain hydrogen, and then also CO2 that is being released to the atmosphere. There are some other technologies like isothermal reforming, but are not that much in use. And as I said, steam methane reforming, it is the most common use technology. There is a special case for steam methane reforming, and it is the one who can capture the CO2 that is being produced in the reaction. So as I mentioned before, in the reaction, it's being produced hydrogen and CO2 in a quite pure way. So it is somehow easy to capture, and that's why people is advocating using steam methane reforming together with CO2 capture and sequestration to produce clean hydrogen. This is what you can see in the literature that is called blue hydrogen. And the truth it is that this process can capture up to 90% of the CO2 produced, but it also has the problem that you have to put this CO2 somewhere else. So this add cost to the process. And overall, we think that in the future, steam methane reforming with CO2, this blue hydrogen I'm mentioning, will be more expensive than producing green hydrogen, the one being produced with electricity and water. And this is the process that I'm mentioning in this slide. You can also split the water molecule H2O into hydrogen and oxygen. And you have different methods to do so. You can use an alkaline electrolyzer. That it is somehow, let's say, a mature technology that is being used for more than 100 years already. You can use a proton exchange membrane. That is a technology that has been developed thanks to the development of fuel cells for the automation. And the less mature technology is the solid oxide electrolyzers that are still non-commercial. You can see there in the right-hand side, this graph shows the number of electrolyzers that has been installed in the world so far. And as you may see, it is a very small installations with just 100 and with efficiency close to 60%. In the right-hand side at the bottom, you can find some figures that I think are very interesting. If all the hydrogen that is being produced today, these 70 million tons, were produced with electrolysis, this would mean 3,300 terawatts hour of additional electricity demand. That means like 10% of the total electricity consumption today in the world, and would be like a significant increase in this electricity demand. Lastly, in the production side, there are some technologies that are under study. One of them that is very interesting is methane splitting, in which you get the hydrogen from the methane and you leave only the carbon, not CO2, but only carbon. That is a solid compound that can be stored much easily than the CO2. It requires a catalyst and a process temperature of more than 1,500 degrees Celsius, so you can imagine that it is not an easy process. And there are some other alternatives that are being under study, but so far are not commercial. So as a summary of this part, let's review that. Hydrogen is a feedstock for the industry that is being produced today, mainly through steam methane reforming that produces CO2, like a country, the total hydrogen production in the world today produces CO2 like a country like Germany. And there are two possible alternatives for making this hydrogen more sustainable. The first one is steam methane reforming with carbon capture and sequestration, and the second one is electrolytic production. We believe, with the number that we have done, that electrolysis will be the most competitive way of producing this sustainable hydrogen. So the green hydrogen, it is what we as group are advocating everywhere. So let's move to the second part, and this is about the storage and transport. Hydrogen is a molecule that is, it travels very, very badly. So it's very difficult to transport. And just to give you an insight, to obtain the same energy as as methane, it takes 3.8 times, close to 4 times the volume of hydrogen. So whenever you hear somebody talking about putting hydrogen into a gas pipeline, you have to bear in mind that for the same volume, you will have 4 times less energy if the gas inside is hydrogen. So it's something to consider whenever any of these applications want to be done. More properties about hydrogen. It is about the cost of compress the hydrogen or to liquefy the hydrogen. So about 7% of the energy content of the hydrogen is needed to compress it up to 200 bars. That is the normal compression pressure. In the cars that in the cars that are running on hydrogen with fuel cells, the standard compression rates are 350 or even 700 bars. If it is a 700 bar, then to compress the hydrogen, you need 10% of the energy content of this hydrogen. If we go to the case of liquefaction, to liquefy the hydrogen will take like 50% of the energy contained in the hydrogen. So you can imagine that any application that uses liquefied hydrogen will have a very, very poor efficiency. So what are the methods that the industry is using today for the hydrogen transportation? Well, first, transmission and distribution pipe network. Transmission pipelines are suitable for long distances, but you need to somehow build dedicated pipelines for hydrogen. When you have small quantities, the more usual way to transport the hydrogen is through compressed hydrogen in trailers. This is what you can see in the roads, and this hydrogen is delivered to a small industry that uses small quantities of hydrogen. When you want to transport big quantities through, for example, through the sea, then you have to go to liquid hydrogen. But as I said, the efficiency of this process is very poor. So is there another way to transport hydrogen apart from compress it or liquefy it? Yes, there are some other ways, and it is to make compounds with this hydrogen and then create a liquid carrier for this hydrogen. These are the what is called the liquid organic hydrogen carriers, or also methanol or ammonia, right? But you can imagine that you have to use a process to link this hydrogen to the other molecules, and then if you want to use the hydrogen, you have to again split the molecule to obtain the hydrogen back. So again, more complication for this form of transportation. So as a summary, compressed hydrogen contains 4 times less energy per volume than natural gas, and this is very important to take into account. Costs are even higher for liquid hydrogen, and the way of transportation depends on the distance and the quantity. So by road up to 300 kilometers, by boat more than 1,000 kilometers. And this cost of transport hydrogen are very related to the way that hydrogen is being produced and used today. So as the molecule is so difficult to transport, what is happening is that the production facilities of hydrogen today are placed very close to the demand side, to the factories that uses this hydrogen. That's why most of the plants of hydrogen are on site the factories that uses this hydrogen. And then hydrogen uses. The biggest demand for hydrogen in the European industry, but it's pretty the same everywhere. It is for ammonia to produce fertilizers, mainly as a feedstock for refineries, and then for other industries. If we want to use hydrogen not as a feedstock for the industry, but as an energy carrier, then we have to look at the other alternatives. So This is a graph that shows what are the costs of storing 1 kilowatt hour, 1 megawatt hour of energy in hydrogen, in batteries, and in pumping hydro. And you can see that the cost of hydrogen is more than double or triple than the batteries and the pumping hydro. So if somebody tells you that hydrogen is a good option to store energy in the future, the renewable energy in the future, just take into account that this should be the last way or the last resource to do it. Because if you have batteries or you have pumping hydro, it's going to be much more efficient and much more competitive to store this kilowatt hour in this way of ways of storage than doing it with hydrogen. Then, as I said before, there are some other uses like natural gas grid injection. So is it possible? Then yes, the answer it is possible. There are some regulations in different countries that allows to have 5% or even 10% of hydrogen in the mix of the gas that it runs through a pipeline. As I said, it's in volume, it's not in energy. But as you can see in the right-hand side, the infrastructure, the gas infrastructure that we have today, it is not really ready for high injections of hydrogen into it. So boilers and kitchen, we only have a tolerance of 20% of hydrogen in volume, as I said before, and compressors will have even less than that. So there are some R&D projects that try to increase these levels, but the truth it is that the hydrogen percentage in energy that can be introduced in the current gas infrastructure, it is really very small. So I don't think this is really an option to decarbonize the gas consumption. If we look at transportation, probably you are aware that there are already some fuel cell electric vehicles. So they are electric vehicles that uses a fuel cell to convert the hydrogen into water and electricity, and then use this electricity to run an electric engine. So the problem with the transportation, it is that the efficiency of hydrogen fuel cell electric vehicle is really poor, because first you have to convert the electricity into hydrogen, and then you have to convert this hydrogen back into electricity. And then the overall efficiency, it is around 25%. If you use this electricity straightforward into the car, then the efficiencies are like 3 times more. So for the same kilowatt hour, you can run 3 times more kilometers with your car. So the point about this, it is that if you can electrify your car, then it is 3 times more efficient to do so than use it through hydrogen. So hydrogen can have a role to play in the transportation, but for those uses that you cannot electrify easily, and we are talking about, for example, trains that doesn't have an electrified line, or long distance freight. So transportation or mobility can use hydrogen, but I would say for a niche. One of the niche markets like long distance heavy transport or maritime. And last, we can use hydrogen in the future as an energy carrier to produce synthetic fuels. So we can produce hydrogen, and with CO2 and with a Fischer-Tropsch process, we can produce this clean electromethane or electrofuels that then you can put into your plane or wherever. You can imagine that these processes are very expensive, and together with the efficiency of burning fuel, this makes that this process and this way of using electricity to produce hydrogen, to produce a synthetic fuel that it will be burned into an internal combustion engine, will be somehow only used for those very hard to electrify uses, like it could be airplanes or very high temperature industries and so on. We have done the review of what sectors could be using this hydrogen as an energy carrier, and overall it could be like 20% of the final energy demand in the European Union. So 80% can be electrified, 20% can be done with hydrogen, and this is why we're interested in this field, because at some point we will have also to decarbonize this 20% of the final energy demand, in this case in the European Union. So as a summary, and this is the last slide, hydrogen is being produced already and is being used in the world already, and it produces a lot of CO2, and there is an opportunity to decarbonize this hydrogen production today, and this is why we are very interested on understanding well how we can decarbonize this through renewables, electrolysis, and providing this feedstock to the industry. Hydrogen as an energy carrier, as an energy vector, could be used to decarbonize some specific sectors, but if you can electrify something, it's always going to be better than use hydrogen because of the efficiency, and this is the physics that is involved in these processes. But there will be energy niche, close to 20%, that can be decarbonized through hydrogen, and it can play a role. So I will leave it here, and happy to answer any questions you may have on this presentation. Well, sorry, before that, just wanted to give you an idea of our Puerto Llano project. It's a project that is going to be developed here in Spain. It's been developed here in Spain. It has 20 megawatt electrolyzer close to a fertilizer plant that produces ammonia. And it will be one of the biggest projects in the world when it's being built at the end of the next year, and will give us insights about how we can develop this technology to supply the current industry of fertilizers and some others. So it has an initial budget of 34 million euros, but the idea is that this will be our big demonstration industrial project that will allow us to understand better how everything works, and then help us to define a future roadmap of hydrogen for the company, for Iberdrola. So thank you, and happy to answer any question you may have about this.
All right. Thank you, James, and to our representatives from Iberdrola for that interesting and informational talk. Now, on to the finals. So please pay attention to this. If we announce your team, please use the raise hand function so we can promote you to a panelist in Zoom. The first finalist team has already been notified. They will begin presenting momentarily. All subsequent finalists will be notified 12 minutes before they are ready to present. Teams, pay attention. Rules for the final round are the exact same as the semifinals round. You will have 5 minutes to present, followed immediately by 5 minutes of Q&A from the judges. An audience question may be taken if judges end their questions before the 5-minute mark passes. We will have a 2-minute buffer period to allow the next team to begin screen sharing. Also the same as semifinals, we'll have a timer message in the panelist chat, 2 minutes, 1 minute, 30 seconds, and they will unmute and say your time is up when time is up. The Q&A will also have a warning at 1 minute of questions left in the chat, and also an unmute for your time is up. I will take a moment now to introduce our stellar final round judges. From Chargepoint, we have Kevin Doyle. From Iberdrola and Avangrid, we have James Rincon. From Saint-Gobain, we have Charles Bateman. And from MIT, we have 3 judges, From the MIT Department of Chemical Engineering, we have Professor Ariel First. From the MIT Energy Initiative, we have Dr. Robert Stoner. And from the MIT Energy Initiative, we have Dr. Lou Carranza. All are experts in energy and technology and are looking forward to seeing your solutions. I will now announce our first finalist team, who will present immediately. They have been given 12 minutes of notice. Our first finalist team from the Next Era Challenge track is Currents of Change. Congratulations. Next Era finalists, you may begin screen sharing after I announce the next finalist. So the next finalist, who will present 12 minutes from now, is from For Your Eyes Only. Sorry, congratulations. So team members from For Your Eyes Only, please raise your hands now so we can promote you to panelists before you are scheduled to go. You are on deck. But now we turn to Next Era. Judges, are we ready? Right. Timer, I assume we are ready.
Kelly, super quickly, I'm going to be sharing the doc or the presentation for my screen. Is that okay?
Yes.
Okay, so let me pull that up super quickly.
Mm-hmm.
How are we looking there?
Good. Let's see, it's loading. Yes, it looks good. And then, awesome. So I guess Currents of Change, I assume your team is ready. Okay, you may begin.
All right, hello everybody. We are Currents of Change, and today we're going to be talking to you about our approach in helping Floridians reduce their carbon footprint, and this is the Next Era project. You can see our handsome faces right there. I'm Casey, the good-looking guy on the far right. We are a ragtag team of freshmen. Rosa and I are hacking from Duke, and Daisy and Hassan are from MIT.
So our problem is that current carbon calculators fail to provide specific and, quite frankly, fail to provide an accurate picture of indirect CO2 emissions. And it is ultimately our goal to help Floridians reduce their CO2 emissions by incentivizing household carbon reductions and also providing good recommendations.
Taking a look at the national greenhouse gas emissions by sector, you'll see that transportation constitutes the largest portion, followed closely by electricity. We also include a graph of carbon footprint by income level to be cognizant of the differential impact by income, as well as providing solutions which are accessible to all. Looking at Florida more specifically, it is apparent that transportation dominates energy consumption with high levels of residential energy use as well, due in large part to cooling demand in the summer. We can see FPL's generation capacity mix continues to be dominated by natural gas, which makes it all the more important to explore carbon offsets. Some demographics which stood out to us were that the median household income in Florida is around $53,000, which we took into account when generating recommendations. Additionally, 58.3% of the population is in the workforce, which explains why transportation is such a big part of energy consumption in Florida due to commuting.
So in the upper left corner, we used the sample customer data provided by Next Era to create a graph of average electricity usage, and this is indexed by month. Next, on the right, we utilized some data analysis frameworks in Python to create a graph that groups together all customers in a specific area code, and then it calculates the average electricity consumption by that zip code. And this database will be used in our algorithm later on.
Yeah, so right here are some existing footprint calculator example. And so, as we mentioned before, it's vague, it lacks the whole picture when it comes to indirect emissions, and also it's not very user-friendly. So that's why our solution is to create an app that users can track their monthly activity on, which then recommends them a tailored carbon offset possibility, and all of which are accessible. And we also include a community aspect where the user is able to compare their past trends and current activity to their neighbors for more incentivization. And so there are 4 key ways in which we are innovating. 1 is specificity, where we focus on the Floridian demographic. 2 is feasibility, as we use income and other factors to make sustainability achievable. 3rd is ease of use, it's an app. And lastly is accountability, as we look at the indirect emissions and give a comprehensive assessment of one's footprint.
So here we have the brain or algorithm on our app. Obviously, it's a lot to take in, so if you guys have any questions afterwards, please don't hesitate to ask. On the far left side of the page, we've got our 4 different types of carbon emissions. This middle section over here is the meat of our algorithm. This is where we take the user input and we convert that into our CO2 emissions, which are tallied in the bottom right corner here. Finally, you can see some census data that we take into account, and here's Hassan's data, the zip code data we saw earlier. This will enable us to be able to compare the user's carbon emissions to that of his neighbors. And all of this is going to get wrapped to be able to tailor our recommendations to the person. So everything you see here is catering to the answers that they provide for us. And one thing that we really wanted to emphasize is that we wanted to make sure that given their income, we're not providing them with solutions that are outside of their budget. For instance, we're not going to recommend somebody who's maybe below the median income to purchase a solar water heater. That being said, in the top right corner, you've got both the financial environmental impacts that you could possibly have in adopting these strategies. For example, increasing your AC by 2 degrees will save 14% on monthly cooling costs.
We've developed many community-oriented recommendations, which we propose to Next Era, and I'm going to focus on 3 of them. The urban forestry program would employ community members to plant trees in urban areas, which will improve air quality and prevent health conditions such as asthma. Next, we have the green and white roofs, which combat the urban heat island effect by reflecting or using the irradiation which strikes roofs, as opposed to traditional roofs, which absorb the rays and heat the home. We hope Next Era would be able to provide the white roof painting service, as this will substantially reduce electricity demands for cooling. Lastly, we have the salt marsh restoration project. Salt marshes are ecologically significant habitats for endangered species, and they also serve as a fish nursery, so they have an economic significance. And there are over 400,000 acres of salt marshes in northern Florida alone. They're very effective carbon sinks, but can be destroyed by storm surges and are worth restoring. So we suggest the development of a Chrome extension, which would notify users of the carbon emissions resulting from their purchases and provide alternatives such as buying secondhand or from a more environmentally conscious company. And we also propose that Next Era include QR codes on utility bills, which customers can scan in our app and track their carbon emissions over time.
So this is a summary of what we just covered, and we thank you for listening to our presentation and are open to any questions that you guys have.
All right, at this point, if judges have any questions, please feel free to unmute and ask.
This is Lou Currens. I have a question. Many of the recommendations seem to be behavioral in nature. And so have you thought through kind of specific incentive structures from the regulators that might increase adherence to the behavior changes?
So let me back up to that slide super quickly. You're proposing that recommendations happen not only on the individual level, but on the level of the companies?
I think so. I'm asking if you've thought about what specific policy incentives would help this.
Yeah, sure. So we kind of touched on this in our previous presentation or our previous Q&A, but there's a lot of financial benefits. So in the top right corner, you can see the impacts that we laid out. This is kind of a win-win situation, right? Because you help the environment out by adopting some of these strategies. But at the end of the day, especially with the ones that pertain to housing and maybe travel, there's a lot to be saved financially. So we hope that the people that would adopt it would know that they're not just doing a service to the environment, but they're doing a service to themselves.
Thank you.
This is Rob Stoner. I'm just trying to understand what quantitative impact you think this will have statewide if you are 100% successful.
Yeah, does anybody else want to take that? I can take that.
Yeah, sure. So a lot of the programs we're suggesting, you can, for instance, for the salt marshes, there's a value not only in preserving biodiversity, which in and of itself confers an advantage ecologically, but for like the cost of restoring it, which is as low as $900 per acre, you can absorb 3 to 5 times more carbon dioxide from the atmosphere than in tropical rainforests. So these particular environments are really effective at absorbing emissions. And so that's why we think that they're worth investing in.
That's not really what I'm asking. I'm asking if you're 100% effective in having adherence among Nextera's customers, what will be the carbon reduction?
Sure, so let me walk back a little bit. It entirely depends to what extent people reduce. So all of these are based off of how above a certain threshold you are and how much do you reduce. So we do leave a little breathing room. Just with the app would give us some area for people to either reduce significantly or reduce, just by bit. Ideally, if people were to, everybody goes beneath the threshold, which would be the median average. The number is because the average Florida emissions is 11.22. Ideally, we could get that and cut by 50% if people are below this median.
I see. Okay, thank you.
Any other questions from judges?
Sure, I have a question. Can you hear me, Kelly?
Yes.
Sure. In climate accounting for like state portfolio standards, are these types of carbon reductions at the sort of personal or
I'm sorry, sir. I'm having a little hard time hearing you.
Sure. Are there any, does the renewable portfolio standard of the state or account for or credit these types of carbon reductions?
James, I think you have to get closer to your mic.
I'm sorry, I've been having
I
problems.
apologize for that.
Okay, can you hear me now?
Loud and clear. Thank you.
Okay, so the question, do the state portfolio standards take into account these types of emission reductions? Are they credited towards any sort of carbon goals that are being accounted for out there?
Sure. Is there anybody that wants to take this one? I can talk a little bit about that. Yeah. So current programs that are within Florida right now don't take into account like these from my research alone. I shouldn't speak for everybody. With the exception of taking into account monthly utility bills, which is obviously something that can be compiled and researched, it would be difficult to be able to see, at least immediately, the emissions that would happen either with the transportation, with shopping, and with waste. Ideally, over time, with enough census data, we'd be able to see like a gradual decrease as people adopt these methods. But it would be, I think, to answer your question, difficult to see, at least from the outright, this being a part of like the state portfolio.
All right, thanks for that. I think we're out of time. So in the interest of that, we'll move on to the next team, but thanks so much for that presentation.
Thank you guys so much. Thanks for listening.
Thanks for judging.
Okay, thank you so much to Currents of Change. Up next, we have for Chevron, Fourier Eyes Only, followed by Jules and Lockdown. If you are in the team Jules and Lockdown, please raise your hand in the webinar. But Fourier Eyes Only, the floor is now yours.
All right. Hello, my name is Yeji Cho, and today we will be presenting our work on Project Aries, responding to the Chevron challenge. I'd like to introduce the other members of Team Fourier Eyes Only. And our project was centered in the Lost Hills oil field of Kern County, California. This field produces 10.6 million barrels of crude oil equivalent per year, and in doing so, uses 94,000 megawatt hours of electricity yearly. Lost Hills purchases its electricity from PG&E, indirectly resulting in 19,000 metric tons of carbon dioxide equivalent emissions. The team's goals within this project were first, to analyze how a switch to solar power would impact those emissions, and second, to develop a plan for emissions reduction and optimization of field operations. Recently, Lost Hills has begun the construction of an on-site solar power generation program encompassing 44,000 megawatt hours annually supplied to the field. Our team analyzed the impact of this project and found that current data is taken in terms of LCFS credits, or the tax incentive for industrial solar power. These credits are not equivalent to units of emissions reduced and therefore provide a less practical assessment of the solar project. Thus, our team used power source distribution data from PG&E alongside the carbon dioxide equivalent emissions per energy source in order to calculate the emissions reduced from a switch to solar. We found that the solar project would lead to a 5,600 metric ton reduction in carbon dioxide emissions, or a 29.6% drop. This number represents great progress, but I'd like to introduce Alec, who will be expanding upon our team's plan to make even greater steps forward.
Thanks, Yeji. So in order to uphold Chevron's mission of addressing climate change by lowering carbon intensity, increasing renewables, and investing in breakthrough technologies, our team considered a variety of major emission sources. First, we looked at Scope 1 emissions, which encompass operations directly related to the oil field. We discovered that unexpected and unaddressed leaks, as well as the venting or flaring of excess methane production, actually accounted for the largest contribution to greenhouse gas emissions from any of Lost Hills operations, more than 3 or 4 times that of just energy usage. Next, we consider scope 2 emissions, which considers the emissions unrelated to the direct operations of the field. So you can think, buying electricity from PG&E rather than using solar energy at night. And in order to address these issues, we created an implementation timeline. First, within years 1 and 2, we wanted to pilot 2 different technologies that we believe can make a huge difference in methane emissions. On the second stage, we want to scale up those technologies and potentially encompass the entire oil field. Third, we want to increase the battery capacity of our solar field production in order to supply more energy into the night. And fourth, considering other ventures that can potentially create more carbon emissions reduced in the future. So in terms of the 2 technologies we looked at, we want Chevron to look at acoustic monitoring sensors and methane detection drones. Acoustic monitoring sensors utilize acoustics or sound, essentially in the drilling wells, in order to determine how healthy the well is, or if there's a leak, or if any maintenance needs to be done. Effectively, methane detection drones act as an everyday kind of detection unit. So they can fly around your field using IR lasers and determining whether or not you have methane leaks. Our plan is to have 50 to 100 of the currently 5,000 wells outfitted with acoustic monitoring sensors and 5 drones used within the first 1 to 2 years in order to determine if these 2 technologies can work synergetically or if one works better than the other. And now I'd like to pass it on to Brent, who will be talking about our long-term goals and how these technologies can be scaled up. Brent?
Thanks, Alec. So right now, currently over 25,000 metric tons of CO2e from methane are being leaked from the Lost Hills site. And this goes against Chevron's goal of matching and reducing methane emissions by 25% by 2023. So what does this new tech mean for Chevron and the environment? Looking forward, in the full scaling of these reduction technologies, maintenance would decrease by 300 times, while also saving the company $5 million per year. Furthermore, the safety of the workers and the surrounding community would be improved, while also reducing over 70% of the methane emissions moving forward. While this was more of the scope 1 emissions, I think scope 2 are also important to consider. So I'll hand it over to Max to go more into that.
Thank you, Brent. So Chevron's current plan to install lithium-ion batteries in Lost Hills is a great start, but by our estimates, the current battery capacity is not nearly enough. So in order to address this, we propose the introduction of vanadium flow batteries. These are far safer than traditional lithium-ion cells. A disaster, or as close to it, would be the formation of harmless chemicals rather than a fiery, violent explosion. Second, vanadium flow batteries are more reliable. They last for over 20 years with no loss in capacity, which is double the lifetime of lithium-ion. And third, they are significantly less expensive. They're rated at nearly half the cost of lithium-ion batteries per kilowatt hour and are far better suited for large-scale storage. And based on our calculations, to accomplish our goal for the next 3 years, which is to incorporate 20 megawatt hours of new energy storage on site, Chevron would save approximately $1.5 million by implementing vanadium flow batteries instead of lithium-ion.
So that's time. Please wrap up your last thought.
Thank you.
And we have a couple of other further technologies, but obviously we don't have any time for that. So some other ideas are electrifying the service fleet and then finding other methods for methane or utilizing the methane released for other methods. But thank you, and we're now open for any questions.
So this is Lou Carranza. You had a lot in there about the methane detection. You had the 2 approaches. You showed some maintenance costs declining. What about the cost of dealing with the methane leaks once they're discovered?
Yeah, so I can take that question actually. So one of the major issues actually currently is that these methane leaks actually do get detected, but they get detected way too late. So you're actually the issue here is not because you're having leaks. Like it's inevitable that you do have leaks, but these leaks are allowed to exist for weeks, if not sometimes even up to a month without detection. So the idea of having these drones and having these sensors is that you'll be able to detect that leak almost immediately, maybe within a day, and then dispatch a team to fix that leak immediately. So effectively, you can reduce over 5 days of methane leaks, which depending on the size of the leak or what well it's coming from, could be tens, if not hundreds of metric tons of CO2 equivalent methane being released. Does that answer your question?
Yes, thank you.
Awesome.
So
we
Alec,
talked
just
about.
oh, go ahead, Charlie. Go ahead.
So we talked about leaks. What about flaring?
Yes, so one of the main issues of flaring, the reason why there's a lot of flaring is actually because the operation of the wells is unoptimized. So sometimes you're actually pulling out too much, your speed of extraction is a lot faster than it should be. So the idea of the acoustic sensor is actually to detect how much or how fast we should be extracting oil. So by being able to monitor that, we're able to optimize the speed so that you actually pull out less oil, or excuse me, pull out less methane. And with less methane extraction, you don't have to flare or vent it. And there's been actually studies in the nearby town of methane emissions, and they're slightly higher than surrounding areas. So one could believe that methane is actually being released or vented, or maybe even flared. So the idea of an acoustic system is to prevent even that excess methane. So any methane that we pull out is intentional and sent to a processing facility rather than having to be flared or released due to an excess. So essentially like a bottleneck.
Okay, thank you.
This is Rob Stoner. What does your title mean? Fourier eyes only?
So it's just our team name. But there's an artist, his album is For Your Eyes Only. And then we kind of threw a pun in there with Fourier, like Fourier analysis and all that stuff.
Is it a pun?
Yeah, it was a pun. It was a pun. Yes.
In what way is it a pun?
The song, this artist, there's a hip hop artist, rap artist, whose album's name is For Your Eyes Only. So it's 4 year. So it's like instead of for your, it's For Your Eyes Only.
So I guess we think of
Awesome.
a pun being different.
Sorry.
Thank you.
I think also James might have had a question.
Yeah, it was just a follow up on Lou's question, really. So I understood the benefit of detecting the leak faster to reduce emissions per leak, but I may have missed how that affects cost of leak detection. So I guess what is the added cost of this program?
Yeah, I can hop in there. So I think one of the biggest thing in terms of the maintenance, so with the drones, you wouldn't have to rely on people going in trucks and traveling over the whole site to, maintain and survey the pipes to see if there's any leaks. And a lot of that cost is decreased by just, automated drones going over and detecting these automatically. And then, furthermore, if you can stop them, sooner, then I guess in terms of environmental cost, less if you can reduce the leakage faster. So more of the cost is, yeah.
Are there FAA regulations that would come into play to add cost, and are those drones restricted to sort of line of sight operation?
So actually, it seems like the operations for these drones in terms of regulation has really been clearing up, and they've been used by multiple other competing companies, it seems. So the gateway to utilizing those is pretty clear. And actually, from our analysis, we thought they'd need a lot more drones, but it seems like compared to what they're doing in surveying right now, just the implementation of 15 drones would really do to decrease maintenance costs.
Thank you.
Thanks for that, for eyes only. In the interest of time, I think we'll move on to the next team. But thanks again.
Thank you.
Thank you so much.
Okay, the next team, as we announced earlier, is Jules and Lockdown for Chargepoint. After that, we will have the green electron. If you're on the green electron, please raise your hand in the webinar. Chargepoint, Jules and Lockdown. The floor is now yours.
Lucy, are you there? Rachel?
Yep.
Hi,
everyone. Oh, go ahead.
Okay, sweet. All right. Hello, hackers. Hello, judges. And hello, everyone watching. We are Jules in Lockdown, and we develop data analytics models to reduce barriers to widespread EV adoption for Chargepoint problem number 2. Lisa, Will, and I are undergrads at Harvard, and Rachel is from University of Illinois, and we are really, really excited to share our idea. Next slide, please. The absence of data analytics despite large increases in electric vehicles, can lead to, number one, lack of infrastructure, meaning lack of sufficient charging stations. And number two, weak grid planning that can lead to issues like an overloaded grid or a duck curve, which we'll explain later. So we can capture data from charging stations and electric vehicles. The question is, how do we use it? I'm going to pass it off to Rachel, who's going to go through some really fascinating data analysis.
Thank you, Rohan. First of all, we analyzed data provided by Chargepoint over a week in October in order to look at a typical week that wasn't during a year of the pandemic. And so if we go to the next slide, we looked at different days in between that week, and you can see interesting trends where there are peaks at certain times of the day. You can see that this graph is not the residential and work graph energy consumption shown over the course of the week is not complementary. So it's not like the residential peaks happen completely at where the minimums of the work are. And so that was interesting. We also saw that there were minimums at about 6 a.m. in the morning throughout this whole week. Can we go to the next slide? In addition to looking at the Chargepoint data, we also looked at Caltech provided Pasadena data where they had about 108 EV charging station sites. And one of the main sites was in the Bay Area, and then the two other main sites were in Pasadena area near Caltech. The left graph shows the charging data, and you can see that there's a significant amount of difference between the battery charged versus the connect minus disconnect time. So you have, you don't need as much time to physically charge the battery versus physically being connected with the charging station. On the right, you can see the California ISO data showing the variations over time of that week in October for renewables generation. And then you can also see the amount of curtailment, so amount of energy that's actually not being used for any kind of purpose. Next slide.
Sorry, I was muted. So this brings us to our solution, which is enhanced vehicle to grid modeling. So the goal of our model is to inform utilities, grid operators, and policymakers, as well as to build stronger incentive programs for EV users to optimize their charging throughout the day. So with our model, there would be vehicle to grid bidirectional charging that would optimize EVSE, which is charging infrastructure, as well as EV batteries on the grid in order to increase grid flexibility, using the data that we previously presented on varying demands throughout the day, as well as capacity remaining in electric vehicle batteries. So by modeling these, we would also be able to evaluate the monetary and economic value of energy storage from vehicles on the grid. And with the projection of EV growth in California, simply in that state by 2030, this would equate to about a value of $26.3 billion US by 2030 as avoided costs from stationary electricity storage.
So like Lisa was explaining, our solution is a dashboard with data analytics, providing data to grid operators. So it comes in two models. The first one is an individual EV model, which is the electric vehicle. It contains two layers, the charging stations and a deeper layer with electric vehicles. And the input would be the battery state of an individual electric vehicle. And another input could be how much more the EV will drive that day. Next slide. So this first model will give an output of the total supply of V2G available for the grid. So the data is then brought into another model where the output is, next slide, is to EVSE operators like Chargepoint, helping to decide whether to charge an EV, which is G to V, or whether to use the electric vehicle as an asset to the grid in G to V, V to G. So this decision-making process will help reduce issues with the duck curve and increase flexibility of the grid capacity.
Oh, we also created a dashboard example of that model as shown here. Next slide.
And we welcome you to view our interactive dashboard by scanning our QR code, which we'll revisit after the end of the presentation. But moving forward, some data that we believe would be helpful in including in our model, which we were not able to source, is the capacity of EV batteries throughout the day, so remaining availability to charge, expected capacity needed for individual drivers, as well as more data for incentivizing level 1 and 2 fast charging over DC fast charging, which results in spikes throughout the grid, as well as the cost of storage at different times of day. So with that, we thank you very much for listening to our presentation. Here are some of our sources, and we will return back to our interactive dashboard. And we welcome any questions. Thank you.
Not everyone wants their EV battery to be used in this way among car owners. Do you have any idea about how that might be taken into account in your models?
Yeah, that's a great question. So we definitely took that into account. And so, of course, participants in the vehicle to grid scheme would be voluntary. And we would also work with stakeholders, including EVSE operators and grid operators, in order to incentivize those who use their charges to participate in our program. So we would also, in addition to sourcing individuals' data from residential chargers, we would also target workplace charging and commercial charging.
Okay.
My question was along the same line, and just a broader, can we have a broader look at sort of the value chain for each of the stakeholders involved? Because yeah, it seemed like, is Chargepoint the one pulling the trigger on, you know, whether it's G to V or V to G, or is that the utility making those decisions based on its needs for the grid? And where's the value in participation for Chargepoint? Where's the value in participation for the utility? And then ultimately the vehicle owner?
Yeah, I can take that question. Lisa, do you mind going back to the model slide, the slide of the model? There we go. Thank you. So if you look at the EVSE model, the second model, you can see that on the input, you do have grid capacity, right? So a stakeholder in that would be the grid operators there. And you also have load demand. So you're inputting into this model, okay, how much energy do we have available? That's our energy capacity. And then you're inputting how much load do we need, right? How much demand is there? And you're outputting to the EVSE operators. That's where their value is on whether we want G to V or V to G, and that's to Chargepoint. Does that answer the question?
I think it does broadly. Yeah. So if you don't, you know, if there's any, you talked about incentives, like what would those incentives look like to the vehicle owner? Would they be payments from the utility to them for each time they engaged in this? Or I'm just trying to understand how that's structured.
Yeah, so I think one potential approach could be providing credits to those who do opt into participating. So depending on how much service they provide to the grid in terms of energy stored, they would also get a credit returned to their utility bill. So in that way, utility operators would be able to kind of be the main point source in terms of the incentive provider. So credits would be one way, and also reduced bills.
Did you include any research on how either light duty or heavy duty fleets could participate?
That's not something that we considered in our model, but definitely something to look into for the future.
Do you say a little more about the nature of your model? Is this meant to be a network model, or is this more of a sort of systems dynamics approach?
So the idea we went after for this is almost similar to a neural model, where you have two layers. You have the initial layer, which is the charging stations, and you have a deep layer, which is the electric vehicles. So I would say, to answer your question, it would be a network model.
All right. Charles, how are we doing on timing?
We've got like 2 minutes left for questions.
Okay. Judges, any more questions?
Can I quickly add on to kind of answer, I think, James' question about the utilities? I think one part that was interesting we found was a lot of the push for the EV research came from the university side, because there's actually the data that we got from the Caltech, there was a lot of motivation for not only their location, but also because recently you can see that LA has committed to zero emission by 2045. And so thinking about that context, they're trying to find ways of trying to get to that zero emission, but also how do we do that economically and affordably? And so a lot of the push comes from policymakers. So that's a lot of the incentive for that, but also research initiatives, and then collaborating with companies that provide that data. So PowerFlex provided that Caltech data, and they're a company that works on EV stations. And so that's kind of like the context from where that data is coming, but also more of the motivation for why there's such research on that.
So can I ask a follow-up on that? This is Ariel. So do you have a sense, or did you get a sense from any of your research about what the buy-in would be from electric vehicle owners? Because it seems like if the main stakeholders are not owners, then it might be hard to get buy-in.
Yeah, I don't know about specific consumer data, but I do know that LA has already implemented, I think, 1,100 more stations in the past few years in Pasadena, Anaheim, LA area. So because, inferring from that, there is consumers trying to adopt more EV. And I think that goes back to the question of the incentives of whether consumers would actually want to participate in such a solution. And I think that would be company on an individual basis, not necessarily everyone participating.
So thanks for that. That's all the time we have for questions. In the interest of time, we'll move on to the next team, but thanks again.
Thank you very much.
Thank you.
All right, next up we have for Saint-Gobain, the Green Electron, followed by Enerhack International. If you're on the team Enerhack International, please raise your hand in the webinar and get ready to present next. The Green Electron, the floor is now yours.
Great, thank you so much. We're just going to be sharing our screen. Awesome.
Okay. So in order to reduce housing waste in the United States, there really needs to be a shift in our relationship with our home. As your needs grow and change, we ask the question, why shouldn't your home change accordingly? We are the Green Electron team, a team of juniors from Boston University, and this is our presentation on Branch, a proposed solution for Saint-Gobain's Design for Disassembly Challenge.
The aspect of the problem that we want to address is excess material waste. Houses get destroyed before the end of their useful life. And after they get destroyed, instead of reusing pieces of them, they tend to get sent directly to landfills. And that adds about 130 million tons of wasted material, which ends up getting replaced by brand new construction. This problem arises because people grow out of their homes. In the US, 31 million people move every year, which is almost 10% of the population. And although not all of those people move for that reason, it's a significant driver. We believe the problem stems from houses not being able to adapt to the changing needs of their owners.
And so our approach is to build reusable, high-quality home modules. These home modules we're able to reuse entire floors because we've designed the ability to detach floors from walls and roofs. We've designed for expansion in that you can add or subtract entire floors of livable space. And we've kept in mind the carbon footprint that our building and the homeowners will have. So we've integrated green heating and energy efficiency measures into our design itself. In essence, we've designed housing that grows with you.
So how are we going to achieve this? Well, here are just 3 parts of the technical side of things. We've thought of a standard combination dovetail and rabbet joint, and that's going to allow you to detach the walls in entire pieces, which was inspired by the company Brica Wood, and you can see how that works in the diagram below joints. We've also decided on a tongue and groove joint that would allow us to detach the roof and add a second story.
We would also be implementing anchor bolts set in the concrete foundation to connect the flooring of the house, as well as radial bolts spread out over the roof ceiling connections to secure those tongue and groove joints, as Keely just mentioned. These standard bolts and sizes would be placed in predetermined locations in order to accommodate the ease of potential expansion.
In addition, we've incorporated the wiring, VRF plumbing, VRS piping, as well as plumbing into the modular unit. And so once you get this unit on site, you don't actually need to worry about doing that rough plumbing and finishing work. You just need to connect it to an electrical line. In addition, we've incorporated a recess in the wall so you can access this and edit it as your time and need changes.
So how do we put these technical components together to create our unique design? In the traditional stick-built home, if your family's needs change and you want to expand your house, you need to leave while invasive and time-intensive construction happens. You ultimately need to pull plumbing, electrical lines, HVAC, where they aren't intended to go. With our design, if you decide that you want to add on to your existing home, you might only need to be gone for the weekend. All you have to do is order another story, employ a crane, and come home to a connected to the ceiling through those tongue and groove joints and fastened with radial roof bolts in strategic locations, as you can see in the diagram at the bottom of the screen. This is what makes the roof detachable and the home itself expandable. There will be some finishing electrical, plumbing, and HVAC work to connect the two floors after they've been added together, but because we've created the central raceway that Gayatri was mentioning on the previous slide to hold all of these components, that won't need to be as extensive because everything comes with the unit. So all that needs to be done is attaching the two. Instead of knocking down walls to expand and add a bedroom, you can literally branch out.
And just as we were talking about accommodating the greater space that a family may need, we also want to accommodate the fact that our planet is changing. And as a result, we want energy efficiency and green heating measures to be incorporated into our building. And so we've incorporated heat recovery, VRF heat pumps, a corrugated metal roof for ease of recycling, as well as basement cold storage as just 4 ways to use the energy around us to make sure that we need to input less energy into our system or into our home.
There also needs to be a large-scale shift in public policy as well as in the mindsets of building companies and consumers and homeowners. Public policy aiding in the cost difference between more sustainable buildings and the current new construction through subsidies will help to incentivize the switch to more sustainable living. Additionally, to further aid in the reduction of building material waste, the mindset of people to see potential in their current homes and the economic incentive of building companies will need to transition to investing in sustainable homes rather than building new construction. The future of the industry is in question. We hope that you, construction companies, and homeowners alike will be able to branch out into a more sustainable future. Thank you so much for listening.
And we'd love to take your questions now.
This is Lou. I have a question. So, zoning requirements and, going from 1-story to 2-story home, that's one consideration. The other thing is it doesn't sound like there's any specialized equipment. Only cranes were mentioned, but is there any kind of manufacturing, 3D or otherwise, like in situ, like on site? Or how do you move the modules from wherever they're built to where they're attached to that existing structure?
Yeah, so I can start off, and Tyler and Keely, feel free to jump in. With the moving the module from one place to another, one of the biggest restrictions we found was actually the width of a flatbed trailer. It was basically how wide the lane is on the highway. And so that's about 8.5 feet. And so most houses are larger than this. And so what we would have to do is have a parting line where we'd actually have a hinge that's able to fold up what a part of the floor would be. So you can actually take the house in 2 components and put it on the flatbed. In terms of specialized equipment, our effect was actually to try to do the opposite. We want to make sure that you can use the technologies and processes that's already used in the construction industry in a different way. So you don't need custom tooling in order to create this sort of system. And so that's something we kind of kept in mind in the materials and the design choices that we chose.
Yeah.
And yeah,
no, go ahead, Gayatri.
I was just going to say, and something Keely mentioned was the standard part sizes as well.
Yeah, exactly. So we really wanted to make sure that the reusability was there. So if a house like this was built 5 years from now, somebody 10 years from now would be able to use that wall piece in their design. So they wouldn't need to deal with new technologies or brand new equipment. And then in terms of the zoning laws, that's another thing that would definitely need to be addressed through public policy and subsidization. So if a municipality were to take this on, they would definitely need to amend their current zoning laws to work with this.
Thank you.
Do you have any information on on sort of the average footprint of a new construction home, or the footprint over the lifetime of a home as it is now, and maybe that you can compare to sort of what that footprint would look like for this solution?
Yeah, so we were working based off of a 2,000 square foot estimate for an average home. And that was based on some office hour help from St. Gobain. So we were working with about 2,000 square feet. And I believe, Gayatri, correct me if I'm wrong, but I believe we were thinking about 800 feet per floor and then 400 square feet for the basement. Is that correct?
Yeah, that's what we were thinking for this design. If you were thinking about the life cycle footprint in terms of use of materials, we didn't have a number on that, but the way that we looked at this was that the idea is that components of this module, as well as the floors and the roof, can be reused at a certain building site, as well as across different buildings. And so you, instead of having to decompose this into its raw materials, you can actually take out a wall and replace that into somebody else's house, or just take out a module and put a different piece in. And so the way that we look at doing that life cycle analysis would have been a little bit different than just breaking it down into raw materials. And so in that way, the way that we would calculate it, our sense of the numbers, although we haven't seen them yet, is that we would be using a lot less carbon intensive processes, because you just need to create these components less often in order to build new constructions.
Have you thought about secondary markets for entire floors? So, instead of this empty nester phenomenon, people would, their kids move out, they just sell their top floor and they can't, maybe they're not as mobile or ambulatory. Could that possibly exist?
Yeah, exactly. That was the subtracting the floors, what we were thinking. The idea that you could then contact the company that you purchased it from, and then you could send it back, and now you would have a one-story house if that fits your needs better.
And the idea is that we kind of get rid of the need to have to downsize a house, quote unquote, and move to a completely different location, risking the property for the next time it's bought being torn down and having a new construction there.
Great, thanks for that. So for the interest of time, we're going to move on to the next team. But thanks again for that presentation.
Thank you.
Thank you so much.
Thank you so much.
Okay, great. Up next, we have for Sterlite Power, Enerhack International, followed by Mardi Gras. If you're on the team Mardi Gras, please raise your hand in the webinar so we can find you. Enerhack, the floor is now yours.
Hi, thank you. Hi, so we are Enerhack International, and we have taken on the Sterlite Power Challenge, and our solution is called Safety Optimization Software, or SOS. Our team consists of myself, Yoni Peleg, Mariko Ogawa, Grace Cassidy, and Tamir Peleg. The challenge that the way we understood it is to increase the behavior-based safety at electric grid construction sites by using digital technologies. And our approach to the solution was to optimize the supervisor's time and improve, therefore, the workers' safety behavior. What that means is that we want the supervisor's decision regarding where to be at each moment during the day to be data-driven and not just done based on intuition. The supervisor can't be at each site at once, so optimizing where to be based on data can increase efficiency and minimize safety risks. Our solution consists of 3 different sections: the data collection, analysis, and resource optimization. We will use cameras at each site that can follow the work that's being done, and then an algorithm can deduce which site is at a higher risk and decide where the supervisor should be based on the highest safety priority. The data that we'll be collecting is divided into 3 parts. We have reports that will be manually inputted into our system, and we'll gather data about each employee. Now, this can be useful because certain employees might be more problematic than other employees, and supervisors might have to be more attentive to those employees. We'll also be using open source data such as weather, that can have a profound effect on safety. And lastly, we'll have a camera placed at each site that will, first of all, feed live imagery to the remote monitor that the construction site manager will have. But it will also allow us to combine different technologies such as QR codes that we can place on safety equipment, and then using machine learning to be able to understand whether the safety equipment is being worn and used, and if it's being used correctly at the site. Our optimization software works as follows. We will give each hazardous parameter will give a weight, and then using known data models such as regression and neural networks, we'll be able to determine the total hazard level at each tower location. Then using that total hazard level, we'll be able to use the weighted traveling salesman problem with a time constraint to tell the supervisor where to be and when based on the hazard level. So how does this improve the safety culture? First of all, cameras. They will completely change the behavior of the employees, but also supervisors that are located at the most critical sites at the most critical time will prevent things from happening before they even begin. We also want to incorporate a reporting mechanism that will use real-time image processing to determine when an accident happens based on a physical flag that can be raised, just like the Andon cord at the Toyota production factory. The camera can detect the flag and then report it to the supervisor. We also want to incorporate an incentive program that will reward those who follow the Andon protocols, and workers will be motivated to self-report. Remember, the more reports we have, the better we can do data analysis. And lastly, on the other side, we'll give a negative ranking for repeated offenses observed by the supervisor. So the cost of this solution is divided into two. We have the physical cost of the physical equipment, but also the engineering cost. The physical equipment is all there, it all exists, and is relatively cheap. It's a one-time expense. But we believe that the engineering cost is what is going to be a bit higher. So we're talking about data analysts and computer scientists. So to sum up, we believe that the solution will both reduce the amount of workplace hazards as well as promote responsible employee behavior. Thank you.
So it seems like the idea is based on the premise that the presence of a supervisor improves the level of safety. Do you have information that validates that sort of assumption?
So we weren't presented with information about it, but in our Q&A sessions with Sterling Power, we were told that the supervisors are a scarce resource and they're more expensive than workers, of course. And if they will be able, they would have more supervisors. So the assumption we made was based on the fact that they need more supervising.
Did you consider the human element and workers' reaction to essentially being, I might call it, spied on with cameras?
So,
you want to go ahead? Yeah.
Yeah, sure. So we believe that that could actually have a positive effect that will cause them to act better because they know that they are being quote unquote spied on. But there's no difference between that and having just a manager there watching them. And it might even be better for them. It will make them possibly feel less like they're being breathed on while working.
Okay, thank you.
And are those cameras installed just for the initial data gathering so that you can optimize where the actual supervisor should be during the times of increased sort of safety hazard? Or are they always installed and someone is always monitoring them in a way? And do you need a supervisor dedicated to monitoring those that then is taken out of the field full time because they're monitoring video full time?
Yeah, this is a great point. So the cameras would be installed for the whole time when work is being done on the tower. A specific site have somewhere between 6 to 12 towers, and the cameras will be monitoring them all the way. The data analysis will be an ongoing process. So we'll have 2 layers that create a schedule for the supervisor daily. And on top of that, we'll have an online live system that updates the schedule and tells the supervisor where to go based on the footage analysis from the cameras. And another benefit from the cameras being present is the ability to open a live feed if something happened and need immediate attention and the supervisor is not there.
So is there a supervisor though monitoring those cameras the whole time?
No, he would be able to if they need, but the cameras will be taking the footage, and a computer analysis will be made on the footage being taken all the time.
Yes. So it's an extra layer for the managers to, if they wanted to supervise a tower from a remote location, they can do that while being at a different tower. If they just wanted to check in to make sure that things are okay over there.
Okay.
All right. Any other questions from judges?
What type of cameras were you planning to use? Was it like wireless and battery powered so that you don't have to run wires?
Yes. So that we found a camera that fits perfectly what we wanted. It's wireless. It can connect directly to 2G or 3G, whatever they have there in the field, and you can connect it to a power storage source. For example, Goal 0 that can work for the entire day. And at the end of the day, there's relatively small cameras. You just pick them up and take them with you, even though it's a remote source, remote area. So it's okay if you leave things in the field.
Yeah. Got it. Thank you.
Great, thanks for that. In the interest of time, we'll move on to the next team, but thanks again for that presentation.
Thank you very much.
All right, next up we have for Iberdrola and Avangrid, Team Mardi Gras, followed by Marginal Utility. If you're on the team Marginal Utility, please raise your hand in the webinar so we can find you. Mardi Gras, the floor is now yours.
Okay. Hello, everyone. It's currently 4:30 a.m. over here. I'm in Beijing, but happy to be presenting for this category. We're Team Mardi Gras, and we're going to be talking about smart DER asset management. So our proposal overall seeks to create a DER integration model using data, community, and financial aspects to unlock the hidden economic value of DER assets currently in New York State. So because of the location of the firm in the downstate New York area, specifically the Brewster service zone, that's what we will be focusing on today. So challenges, as a whole, DERs are basically disruptive for the traditional utility model of procuring power from generators and sending it to consumers because, they create two-way distribution, they create storage, they create, more supply and demand uncertainties. And so, that disrupts the traditional utility model, but it also, because they have value, they're an asset, they can provide an opportunity to have new service economy through cheap energy and data collection. The challenge, of course, in this specific area is that because upstate New York has saturated renewable development and stabilizing energy demand, that actually reduces the potential for this demand for grid services. So we choose to focus on the Brewster service area, which is the only place where the firm operates in downstate New York, where there will be increasing installation rate, increasing demand for the service group. So basically just looking at the Brewster service area, it has a high solar PV and EV concentration, about 140 megawatts of solar installed, 30 megawatt hour storage deployed, higher proportion of Tesla superchargers, and other benefits. So it's favorable policies and a good investment environment mean that we'll see increasing amounts of solar PVs and storage and EVs in the future. It's higher income, so you're more likely to see like smart assets and smart homes, things that we can leverage. And then it's less rural, it's has less, so that means there's less distance between solar panels. When we talk about aggregation, we'll discuss why this is important. And finally, it has a relatively high hosting capacity, which means we won't have to think about other infrastructure investments. I'll turn it over to my colleague Ken to discuss that.
Yeah, thank you, Kevin. So an important thing is that we're not interested, or excuse me, we're not pitching the deployment of more resources. What we're pitching is really the asset management of all these distributed resources. So we think that by looking at the aggregated solar in this area, we can leverage the resources for, for the private investor, the homeowner who has put all this money into their storage system, their PV system, to help them maximize the value they get out of it, but also to help the utilities coordinate in a way that you would see in like a cooperative utility. So one of the parts of that is a digital app solution or platform. So one of the things that I think a lot of users would be interested in are the daily usage and the variable pricing that they would see through the market. And really understanding, how can they benefit the market as a whole. I think you look at it and you say that it's really a partnership. It's not that the utility takes control of the assets and deploys them at will in a way that doesn't help the consumer, but a way that they share responsibility to make market pricing more efficient, and it really gives the market a chance to take the benefit of the renewable resources that have already been deployed. And again, a little further on leveraging that. So you'd see things like how can we get collective bargaining agreements to bring more solar onto the grid or more storage on the grid? How can we get more collective bargaining for preventative maintenance? And really, when you look at a homeowner who has solar and who has storage, they don't really have the tools that they need to make the most of those assets. So how can the utilities help those folks while also, using the power to benefit the market? And as far as monetization, we see a couple of streams that are really obvious. We see market arbitrage. When you look at on versus off-peak pricing, we see about 120K a year opportunity for this market specifically. And we talk about frequency regulation and the capacity market. We look at regulating reserves. We see about a $320,000 per year opportunity for the distributed solar that's already in place to be monetized.
So overall, if we're looking at the benefits for the firm, for example, for earnings adjustment mechanisms, which you can basically apply to the government for, we think that a way to propose that is to apply for them on the basis of per added DER to the smart grid, based on an estimated service fee, which we plan on waiving for people in this region to join. And this can phase out over the 5 to 7 years as efficiency gains catch up. The goal is that we want to onboard as many DERs as possible to get these data points. We also have like NWAs from capital investments. These are basically like, opportunity costs you don't have to pay for extra transmissions. So for example, from up downstate New York is exceedingly difficult constraint.
So that's time.
We out of time.
Your last thought. Yep.
And then lastly, like there's no extra infrastructure costs for the project because all of the technologies required to create this smart aggregate solar community are already being implemented by the firm in their DSIP. Their implementation plan, and that would utilize the technologies we list here. These are basically technologies that are already in play that are planning to be finished within the next 5 years in terms of implementation. But yeah, sorry, went a little bit over. But well, yeah, we'll take some questions now, I guess.
What sort of loads were you thinking of bidding in for frequency regulation?
Oh, sorry. Ken, do you have that?
Yeah, sorry, was that James?
That was Kevin that asked the question.
Oh, sorry, Kevin, I'm trying to get through Zoom. Yeah, so I think, the really obvious thing when you talk about arbitrage is, you charge off peak at, let's say, 3 o'clock in the morning and the wind is blowing and you discharge at the morning or the evening peak, or maybe you can make a dual play on the day.
No, I was asking about frequency regulation.
Could you ask the question again? I'm sorry.
I was asking about frequency regulation.
Sure.
What loads are you thinking about?
as far as the timing of the loads or the amount of, or the size of the loads, or what's the?
Yeah, my understanding is that frequency regulation requires very quick turnaround from the time that they issue a request to the time that you actually have to drop load. It needs to be very quick.
So I think one of the important things here, when we talk about distributed assets and management, we talk about control, right? So if we have a typical house as an example, and they have storage, how do you signal or allow them to come onto the grid, right? How do you allow, if they opt in this DER, the idea is the utility will take the digital asset management and they take control of that asset. So that control, I think, takes a lot of trust. But really, when we look at these consumers that are already sticky with installing these expensive systems in their house, we think that there's a larger social mission, and there are people that want to see a more efficient marketplace, less variable pricing, less peaks and valleys, and more of a steady kind of stream of pricing that also removes the hedging, so that you don't have to worry about, if there's a fixed rate, here's my overhead, here's my room to kind of make the most out of this and not lose money. I'm not sure if that answers your question or not.
No, it's okay. Thanks.
Thank you.
Do you have anything to point to show whether this increases or decreases the payback period for asset owners?
So, I mean, it should decrease the payback time because you're essentially unlocking the asset, right? So you're making it, I mean, because of the way that we're charging them, like we're trying to waive the service fee, we're trying to take it out of their hands. Like even incrementally, the money they owe, the money they owe will allow them to pay it back faster. The goal is to make it easy for asset owners to contribute, their devices.
And you actually, to couple that kind of question, James and Kevin, I'm sorry, I'm trying to survive this 48-hour hackathon. But so if you look at a house that maybe has a 25 kilowatt hour capacity a day and they only use 20, then really we're trying to help out those asset owners. And how can they monetize the last 5 so that they're not wasting the reserves of the battery or the solar channels, and they're actually able to participate in the market in general. And as far as discharge rates, in the capacity market, especially in New England, you see a lot of traditional heavy oil or heavy coal plants that require a day ahead startup time because of the steam production. And really with a battery asset that's digitally controlled and distributed, you get instant access to the grid and instant decharging of those assets.
And there are a lot of value streams that you point to in this, which I think is a good thing, but it raises the question as to, how difficult is it to optimize, because you have to, bid into these markets to provide a certain amount of capacity. So how do you make sure you're optimizing the use of these assets when, if they're aggregated, you need to bid part of them to the frequency market, part of them to the wholesale market, and reserve some of it for residents to receive net metering or something like that?
Yeah, I think that's a great question, James. With a traditional solar without storage asset, power just flows, right? The sun shines, power has to go somewhere. It can't be made in a vacuum. I think that data is our friend here. I think that data can help the consumer and the utility kind of balance out the load and figure out when to actually buy and when to actually spend the energy. So, again, I think the platform, the access, and building that trust link between the consumer and the utility to have this data available and to form that partnership for the revenue stream is where the gold lies, as far as utilizing these assets and really making a difference as far as how they're used and how we make a more sustainable future.
So thanks for that, Mardi Gras. We're out of time. So in the interest of that, we'll move on to the next team, but thanks again.
Yeah, thanks a bunch.
Get some sleep.
Okay, coming up next for Macquarie Green Investment Group, we have Marginal Utility. This is our last finalist. Marginal Utility, the floor is now yours.
All right. Hello, we are Marginal Utility from Stanford University. I am Will Butcher, along with Chris Hull, Juliana Luyang, and Kailash Rama. We want to begin with a brief framing of the challenge. As penetration of solar on the California grid increases, zero marginal cost solar generation results in lower power prices, particularly during the middle of the day when solar production is highest. This solar value deflation poses a significant risk to the economics of new solar development. At the same time, high penetrations of solar create a duck curve in which the net load required by non-solar generators experiences a trough in the middle of the day and a sharp ramp in the evening. This increases the value of flexible generation and storage. We have divided our solutions to this challenge into near-term and longer-term solutions. In the near term, we propose reducing merchant risk for solar in wholesale markets through development of hybrid solar plus storage projects. In the longer term, we propose a set of market and regulatory policy changes that will enable the integration of higher penetrations of renewables on the grid. Our near-term solution proposes to co-locate solar and lithium-ion batteries at a single point of interconnection in order to reduce wholesale revenue risk for solar and realize cost and revenue synergies. Cost synergies from co-location include the investment tax credit, which is available to storage that charges from solar, reduce capital costs through shared permitting and siting, shared power electronic equipment, and shared interconnection agreements, as well as reduce transaction and administrative costs. Revenue synergies result from the ability to capture otherwise curtailed solar generation. In addition, while solar revenues are inversely correlated with volatility, which increases at higher penetrations of solar, storage revenues are positively correlated with volatility. So the combination of solar and storage reduces overall risk. Potential dyssynergies of correlation include operational constraints on the battery, as well as suboptimal battery siting. I'll turn it over now to Kailash to discuss our analysis of solar plus storage economics.
Thanks, Will. So we constructed a revenue forecasting model to better understand the economic implications of combining solar and storage. We started by modeling revenues which PV and storage can earn on the CAISO marketplace. Using CAISO NP15 2019 data as a reference case, we constructed some illustrative power pricing scenarios for years 2030 and 2045. Then we used a dispatch model to calculate merchant revenues in these new forecasted prices with greater intraday volatility. For storage, this dispatch model became a little complex as we had to co-optimize in the day-ahead energy market between energy and ancillary services revenues. The results of that dispatch model and the price projections are shown on these graphs on the right. Ultimately, our results show that storage can serve as an effective tool for mitigating merchant risk on utility scale solar projects. The revenue stack projections on the left show a significant decrease in projected solar energy revenues over the next 25 years. Simultaneously, however, we see that storage revenues, the right side columns, remain relatively constant throughout this time period. This is largely driven by an increase in energy revenues, energy arbitrage revenues, which simultaneously takes place with a decrease in ancillary services revenues. This overall results in value added to the solar plus storage project. We see that a solar standalone project has an unlevered IRR of only 2.5%, but when co-located with storage, that can be increased to 10.6.
For our long-term solution, we propose that Macquarie focuses their efforts on pushing incentives for storage, legislation that permits interstate transmission, and incentives for demand response. We want to highlight that storage incentives and transmission add additional revenue streams and increase the potential market for renewable generation, respectively. Storage incentives also synergize well with our short-term scheme in terms of de-risking the operations. Demand response actions such as real-time time of use tariffs would help flatten the duck curve and decrease the variability in pricing and help increase the value of solar and long-term penetration. Thank you for listening to our presentation.
All right, do judges have questions?
Sure, I have a question, guys. How regional is your data? Is this only true for the California market, or does this analysis hold up in parts of the country where the price curves are, you know, maybe significantly different?
Yeah, I can start off, and if others want to add in. So this phenomenon of intraday prices significantly decreasing in wholesale markets due to the penetration of solar is something that is seen across markets. We've seen this in CAISO. There's also a similar phenomenon that has been observed in NEM in Australia's wholesale market. And it's something we would expect to see in other parts of the world.
Awesome. We can also take Q&A from the audience if no judges have questions. If anyone wants to submit a Q&A.
I have another question if there's not one. So it was thought given to the addition of storage making these solar installations look more like firm generation assets, and is there any premium put on a firm asset versus an intermittent asset?
Yeah, I can address that. So we considered that, and that was part of our rationale for modeling solar and storage standalone, because you could develop them as separate projects rather than co-locate. We're not currently aware of any compensation for, you know, combining them into one project that has a more of a baseload type profile. But one thing we considered was with the rise of corporate off-takers looking for 24/7 renewables, that you could potentially market a product like a 24/7 renewable PPA.
Yeah, and just another point to add there. I think increasingly, you know, shifting towards a more baseload renewables generation profile will be advantageous in terms of capacity revenues. We're already seeing in many wholesale markets a decrease in compensation for capacity for renewables projects due to their intermittency. And so as those regulations become even stricter, then yeah, incorporating storage will become all the more important.
Great. We have a question from the audience. Kathy Wang is asking, how do you project out future energy prices?
Yeah, for the purpose of this analysis, we did not build a capacity expansion model or anything complicated like that. We attempted to create scenarios that would incorporate the expected decrease in average power prices, as well as increase in the volatility of power prices as the penetration of solar increases.
All right, and I guess one more question from the audience. Dia is asking, what will be the fixed costs associated with the solar versus storage, especially in comparison to solar only?
So,
yeah. Go ahead.
So we actually did not incorporate any fixed cost operating cost savings. We took the estimates from the EIA for annual operating costs for solar and for storage and just added them together.
Okay, great. That's all the time we have for questions. So I think now I'll turn it over to Kelly, I believe.
All right. Wow, we made it. Thank you all for your great presentations. We recognize the time zone difficulties and commend everyone for working hard. So the judges will now go into a separate room to deliberate. Hackers, you can stay tuned for the closing ceremony, which will start at 4:45 p.m. Eastern Standard Time and occur on the same Zoom link. This is when we will acknowledge each track winner and runner-up and reveal all other prize winners, including raffles from Charge Days, puzzle challenge winners, and last but not least, the first, second, and third place grand prize winners from the hackathon. We will see you back on this same Zoom link at 4:45 p.m. Eastern Standard Time. And a note that this is also being live streamed to YouTube and will be kept up on our YouTube channel afterwards if you have your time zone constraints. So see you back here at 4:45. Thank you all. All right, hello hackers. Welcome back and welcome to the final and perhaps most celebratory event of the 2020 MIT Energy Hack, our awards ceremony. We hope that our 6th annual and first virtual edition of MIT Energy Hack has provided you with an opportunity to learn about what challenges energy companies are facing today. We also hope it gave you the chance to work with other students passionate about energy. These challenges are not easy, yet it is as students that we can begin making a difference and moving our world towards a sustainable energy future. Through engagement, innovation, and impact, we hope this event has provided you with a chance to continue collaborating with the global energy community during unprecedented times. We had 64 teams present this morning, which means teams spent collectively over 2,300 hours working on solutions this weekend. This is not even multiplying by the number of people on each team. That is a feat to be reckoned with. Before we get started on the finals, I want to provide some tremendous thank yous and acknowledgements to everyone who made this event happen. First, a huge thank you to all teams for participating. This means you in the audience. Your energy and dedication to this hackathon is the spirit that keeps it alive. Please get some sleep after this weekend and keep an eye out for 2020 Energy Hack swag coming your way and a certificate of participation as small tokens of gratitude. Second, thank you to all sponsors, Saint-Gobain, Iberdrola and Avangrid, Chargepoint, NextEra, Macquarie, Green Investment Group, Sterlite, and Chevron for dedicating your weeks and weekends leading up to the hackathon for coming up with a challenge statement, participating in coffee chats, answering questions in office hours, and judging the solutions today. The companies are at the forefront of energy innovation, and it's an honor to have each one of you. Thank you also to our internal sponsors, MIT Department of Chemical Engineering, MIT Department of Physics, and MIT Environmental Solutions Initiative. Thank you to the Rotary Club of Mayfair for our special partnership and a sharing of a common mission to educate. And thank you to our volunteers who helped time during rounds. Third, I want to say a thank you to our finance judges, James Rincon, Charles Bateman, Kevin Doyle, Professor Ariel First, Dr. Robert Stoner, and Dr. Lou Carranza. Your expertise and your time are much appreciated. Finally, I want to say thank you to our incredible organizing team. Since June 2020, they have worked tirelessly, even amidst busy schedules, to put this entire event together from start to finish. I want to shout out each of our individual teams. From internal sponsorship, Andrea Lowe and Shreya Vangra. From our marketing team, Danica Dong and Ariel Fuchs. From our communications team, Irina Katimsky and Peter McHale. From our corporate relations team, Charles Wan, Vikram Sharma, and Tejas Chafakar. Finally, from our operations team, Michael Chang, Ragni Srinath, and Sarah Lomar. You all are the absolute best, and it has been a privilege and an honor. Another note, this is our first time going virtual, so we are still growing and improving. We encourage you to submit feedback to the event when we send out emails. We really appreciate your participation and hope you had as much fun participating as we had running the event. With that, the Energy Hack organizing team will announce our prizes in the following order. We'll have gag prizes first, then raffle prizes, then theme prize winners, then finalist and runner-up acknowledgements. And finally, our grand winners going in 3rd, 2nd, and 1st place. With that, I'll turn it over to our organizing committee to present the prizes.
Hi everyone, the first prize we're going to announce are the gag prizes. Before we do that though, the organizing team would like to give a huge thank you to Kelly Wu for being the most incredible central director we could have asked for. She's been leading this team through unprecedented challenges with the virtual environment. And it was not only a team effort, but a team effort directed by Kelly that made this hackathon possible. So thank you very much on behalf of the entire organizing board. So our first gag prize that we will be presenting today is the best team name. Now, a little disclaimer from the organizing team, we do not actually have any physical prizes for any of our gag prize awardees. You do get bragging rights for probably the rest of your life though. The best team name is Big DK Energy. Congratulations. And did we mention that they're actually from Denmark? Very creative. We were all very impressed when we saw the team submission come through the first night. And we knew you all had to win. Our next gag prize is the earliest submission. We were also very impressed by this team. Team Quadra Power submitted at 8:08 a.m. Eastern Standard Time. I don't even think I was awake then, so congratulations to you. Now Andrea will take on the next gag prizes.
All right, so for our next prize, we have highest slide count. And that goes to UBC Smart City with 22 slides. Congratulations, and I still wonder how you got through 22 slides in 5 minutes. Good job. And our final gag prize is for most events attended. So we had many events over charge days, and we'd like to recognize the following person for attending the most events. Tobias Kerrigan, hands down, went to most, if not all, of the events. And congratulations to all of the gag prize winners for getting lifelong bragging rights.
All right. I will be announcing the raffle prizes. These are our actual prizes, and they are awarded per raffle basis to those who attended our Charge Days events. So the first prize on Monday goes to Dilaj Raj Sin. Thank you very much for coming and showing us your face very early in the week when the hackathon was still very far away. Our next prize for our Wednesday events goes to Manuel Morales. Again, thank you so much for your support. We really appreciated seeing all the hackers at the Charge Days events. And our final raffle prize for the Thursday Charge Day goes to Almas Kaptagayev. Thank you to all the hackers who showed up, and we hope that you enjoyed the Charge Days programming.
Okay, now for puzzle winners. First, for the Chargepoint puzzle, we would like to recognize Mustafa Arman Kandemir and Onur Öztürk. Secondly, for the Iberdrola and Avangrid puzzle, we would like to recognize the team Bilal Kamal, Lisa Potemkina, Abhijit Nikare, and Tobias Kerrigan, as well as an individual submission from Johannes Enolander. And lastly, for the Saint-Gobain puzzle challenge, we would like to recognize, again, Lisa Potemkina, Abhijit Nikare, and Tobias Kerrigan. Congratulations.
Next, we'll be announcing our theme winners, which were chosen by our organizing team. First, we have Most Out of the Box, which will go to UBC Smart City. And then next, we have an award for the most community-oriented solution. And then lastly, we will be awarding the best visualization to Team Tech Support.
Congratulations to all our round one runner-ups for participating. Our judges really liked your work as well. And although you are not in the finals, you were almost there. So we do want to recognize you for the wonderful work that you did over the weekend. And of course, we will be remiss if we don't acknowledge our finalists. Thank you so much for sticking it out right to the end and giving us such great work. So much so that the judges had to deliberate for a long time to decide who the winners were. So thank you so much for being here and participating and contributing to Energy this weekend.
All right, I think now is the moment we have been waiting for. So how grand prizes will work, Shreya, correct me if I'm wrong. So we will go in reverse order. So third, second, and then first place. And our sponsor judges will be announcing the winners, but Shreya will also follow up with remarks that they would like to give to each team. Is that correct? Okay.
So in third place overall, we have Jules in lockdown. Congratulations to all of you.
Congratulations. And as Kelly mentioned, I'm going to be reporting some of the comments the judges made as a group during deliberation that they really would like these teams to hear. So first off, some general comments about all of the finalist teams and all of the hackers. All of our judges thought the presentations were very well thought out, very well presented, and they were incredibly impressed with the number of great startup ideas that can come out of this weekend. For Jules in Lockdown, our judges are experts and have a lot of experience in the current and future directions of the energy market. And they believe that the ideas of this team were very applicable in the real world and that their concepts are coming now and being implemented or being implemented in the near future all around us. And they're excited to see how this team can take this incentive model with a focus on marketing and expand upon it going into the future and past this weekend. So congratulations again to Jules in Lockdown.
Second place, the team they call Currents of Change. We thought they did a great job. Second place, very nice. And we want to say thanks again to all the MIT organizers who put this amazing program together, virtual for the first time. And congratulations, MIT, congratulations, Currents of Change.
Thank you very much for those kind words, James. The same said, second place goes to Currents of Change. As for the judges' comments, they noted that Currents of Change had the most original idea and deliverable. They had such a diverse array of solutions for the problem they identified, and the judges even noted that they might not have thought of all of the different solutions this team proposed if they were hackers at this hackathon. They think this team has a very attractive startup potential with their idea from this weekend, along with their very well flushed out app, and they're very excited to see how they progress on this deliverable. Congratulations again to Currents of Change.
All right. And for the grand prize winner for first place was Marginal Utility, the group that competed on the Macquarie Green Investment Group Challenge. Great job. This is a really solid presentation and we just loved it. Yeah, so congratulations.
Thank you, Kevin. Again, congratulations to Marginal Utility. I think we can't underemphasize how well put together and presented Marginal Utility was. Some more comments from the judges are that Marginal Utility made remarkable progress on developing a model that produced quantitative results in such a short time frame. They are very impressed with this team and are looking forward to how they continue to develop their product past this weekend.
All right. Thank you all to the judges for our sustainability circle sponsors. For announcing our winners. A huge congratulations to everyone, from gag prizes to theme prizes to most commendably our first, second, and third place winners. Just one more thing, if you've won a prize, we'll be in touch. We are honored to have been able to host you and witness your incredible innovation this weekend. Don't let this energy fade away. Good luck as you continue working towards the tough but needed solutions for an sustainable energy future. It's been an honor and we hope to see you again next